So, hello, good afternoon. So, for this meeting, I want to actually, like, gusto ko lang din naman kayong kumustahan. Kung, well, we're technically by the middle of the SEM. Hopefully, you're all doing okay. Hopefully, walang natatamaan masyado sa inyo with anything. Hopefully, you're all healthy and doing well. If not, sabihin nyo lang. Let's see what we can do. Anyway, moving on. Main agendas for today's meeting will be one, yung problem set. And siguro may personal tips na rin for you to make habol sa problem set na may deadline. And then number two, materials for weeks 7 and 8. So, we acknowledge that na medyo nagkulang kami sa week 8 materials, medyo nahuli siya. Although, release naman siya now. Hopefully, hindi kayo masyadong naguluhan about that. And, yeah, moving on. So, the problem set, the quote-unquote deadline is on May 9. But, of course, if you are experiencing some things, if you have some problem or may iba kayong kailangan gawin, it will be very much okay to submit later. Just inform us or at least ako. Just inform me that you will be submitting late so that basically hindi tayo naghihintayan basically. So, as you may know, yung problem set natin has 4 parts and each part actually has corresponding topics per week. So yung part 1 covers weeks 1 and 2, part 2 covers weeks 3 and 4, part 3 covers week 6, and then part 4 covers week 7 and 8. So I know most of you okay naman na sila sa weeks 1 and 2. And then pagdating sa weeks 3 and 4, medyo kalahati pa lang ata ang may magandang progress. Actually, wala pa yata ang kalahati. Ang alam kong kalahati na is umaabot sa week 6. So, yeah, meron sa inyong nakita kong nag-skip na week 4 and that's okay. Actually, we're still discussing on doing some modifications doon sa submissions for weeks 3 and 4 so that mas madali kayong makakatch up. Then lastly, since yung part 4, medyo nagka-problems kami dun sa release niya. So we're making it optional since late siyang nabigay. But then again, hopefully you can look at the problems. Actually, ako yung gumawa. And then, ayun, it should help kumbaga summarize yung para saan yung pag-discuss ng week 7 and 8 topics. So yeah, silipin lang natin per part in hopes of giving you a preview noong gagawin or hopefully if meron sa inyo may questions, they should be able to ask as we see the question. So yung first part is just analyzing some code. So you just have to identify the following given this. So basically OOP in Python. So just make sure you know what each of these things are and you should be okay with that. Then the next part here is to basically identify the big O notation of the following functions defined over here on the left. So merong 10 functions. Hold on. Yeah, so there are 10 functions over here. So ang kailangan nyo lang naman gawin is to basically give yung big O time complexity ng mga to. And then hopefully okay. kaya nyo naman na siguro yung mga yan. So, one main thing for big O notation is to, pag meron tayong loops na ganyan, determine how many iterations yung gagawin doon sa loop. So for example, pag range n, yun yung pinakamadali, we just say n times pag nasa range. Although, for example, dito sa function 4, meron tayong break statement sa loob ng loop. So, baka hindi siya exactly n. So, tignan nyo na lang. You can always type these in your interpreter or wherever you can find a parang magra-run ng Python script for you. And then, you can always just count yung number of times na mag-print siya or something. Although, that's not always the best case to calculate it. Actually yun, kailangan yung tingnan kung how many times talaga magra-run yung isang loop. So, then for example, dito sa function 6, hindi tayo range. So, for loop siya in a list of length n. So, how many times mag-iterate yung for loop if meron akong list of length n. Then, this one, function 7, as long as n is positive, mag-run yung loop. And then, after every loop, n is divided by 2, tapos nag-add tayo ng 1. So, ilang times mag-run yung loop. So, a good way of testing it is, for example, you have n equals 10, tapos i-tabulate nyo yung data. So, the first part, n equals 10, positive siya. So, papasok siya dun sa loop. Tapos, yung bagong n value will be, so, 10 over 2 plus 1. So, magiging 6. So basically, i-list down nyo lang starting from the n na ginawa nyo initially. Tapos bilangin nyo kung ilan beses siya magra-run. Then usually, you can find yourself an expression determining yung number of times na mag-run given yung initial value na n. Then, I don't think there's much else for that. Then, lastly, this. So, what is the big O complexity of BOGO sort? So, sa mga hindi pa familiar, yung BOGO sort is a sorting algorithm wherein basically, isa-shuffle mo yung number of elements, and then as long as hindi pa siya sorted, mag-shuffle ka na mag-shuffle. So, imagine you have a deck of cards. So, isa-shuffle mo na siya na isa-shuffle hanggang makita mo na sorted siya. So, obviously, hindi siya mabilis. And quite in reality, baka hindi nga siya mangyari, pero pwede siya dapat mangyari, assuming all cases of shuffling are possible. So, if, for example, ang BOGO sort assumes na given at each iteration, mag-a-assign ka ng random indices for each item. So, if dadaanan mo naman lahat ng possible indices, there should be one instance na sorted yung list. So, ayun na. So, medyo konting probability to. So, you may want to look into that. Then, ito, may modified BOGO sort na may buckets, I see. So, yeah. Kaya nyo na yan. So, that is for problem set part 1. For problem set part 2. So, ito yung actually, looking at yung mga nandito, baka mas madali pa actually sila doon sa exercises sa week 4. So if you want, you can start doing these first. And then pag nakuha nyo na yung tamang sagot for the problem set, which is yung may deadline, and then baka mas madali na for you to do yung week 4 exercises if meron ka nang nagawang for sure na natama mo na. So, I think napakita ko din to dati. The first function is a generic common function loop. So, I guess yung hint dito is yung initials nung problem. And then, ang titingnan nyo lang dito, ano yung pwedeng gamitin na loop invariant. So, for sure, before determining a loop invariant, you should have a good idea kung anong ginagawa ng function. So, from there, kailangan mong mag-state nung loop invariant mo na eventually magli-lead doon sa sagot na yun. So, for example, kung yung function ko generates the least common multiple of A and B, so probably yung loop invariant ko would be something like a temporary variable being the least common multiple ng subset ng problem. So instead of A and B, parang A and I or A and Y. So basically, yung loop invariant mo parang subset or parang smaller version siya noong gusto mong mangyaring sagot in the end. I think mas kita mo yon. For example, if we go to na sorting algorithms dito and then look at so let's see bubble sort. So ang bubble sort mo is meron siyang dalawang loops, di ba? So pag natatapos yung inner for loop, we have a part noong list natin dito on the right na iba yung color. And that's because may certain property yung mga objects natin na nadaanan na. So parang makita mo dito, yung colored part natin on the right side is already sorted and then meron tayong unsorted na list. So for bubble sort, yung outer loop invariant natin, since yung goal natin is masort yung buong array, yung loop invariant nung outer for loop natin is to our states that part of our array is sorted. So yung loop invariant natin will look something like tapos ko yung notepad para ma-type ko siya out loud or ma-type ko siya. Kaya na ba yun? So a good loop invariant for a sorting algorithm. So isang slice tong array, maybe from, so in this case, I guess may counter tayo. Pag meron na tayong after 1, meron ng isang nandyan. So hanggang dulo siya ng list. So from let's say J hanggang dulo ng list is sorted. So yung J natin magsa-start siya at let's say n-1 and then bababa siya hanggang 0 so that pagkatapos nung algorithm natin at termination, J equals 0. So ang magiging itsura ng loop invariant natin, A from 0 to dulo, sige lagay ko na lang, J hanggang N is sorted. So knowing that ito yung gusto nating end condition, kukuha ko ng partial parang subset noong gusto kong maging solution niya in the end, which is ayun. So, imbis na buong array, a part of the array starting from J and then ending at N. And yun pa lang yung sorted. Kasi yun nga, we want the loop invariant to be true at each step noong algorithm or each step ng loop. So, hindi naman sorted yung buong loop pagka-start nyo pa lang. So, parang little by little, sinusort natin yung buong array. And then, siguro mas makikita natin yun sa selection sort. So, dito sa selection sort, hinahanap natin yung minimum value doon sa inner loop. And then, ilalagay natin siya doon sa current na counter natin. So, not sure. Sabihin natin yung counter niya is I. So, from the start of the loop hanggang I, sorted. So, in this case, nakakatatlong run na yung loop. So, meron na tayong 3 numbers na sure tayo na sorted. And then, it starts from 0 hanggang 3. And then, eventually, is makakarating siya sa dulo. So, yun yung sa outer na for loop. So, usually, pag sa inner na for loop, it has something to do with minimum and maximum numbers. So, in this case, sa selection sort, I think na-discuss nyo naman to. Yung inner for loop nyo finds the minimum number. So, minimum number doon sa unsorted na list. So, from 36 to 48 dito, ang inner for loop, hahanapin niya yung minimum na number, which is in this case, 26. And then, ilalagay niya siya doon sa sorted na list. So, ang parang premise kasi dito is we have a already sorted na list. And alam natin that they are either the minimum or the maximum so far nung daanan mo. So, yung sa loob, yung inner na for loop finds the minimum element. So, kung nahanap ko yung first 3 minimum elements, nandun sila sa first 3 na locations nung list. So, yung next minimum element, susunod lang sa kanya doon sa list to maintain yung sorting. So, ayun. So, ano yung magiging loop invariant ng inner na for loop? So, yung, ayun, actually, obvious naman dito, yung current minimum, siya yung current minimum doon sa list. And gusto mong ma-determine, siya yung current minimum doon sa buong unsorted na list. Kasi, chine-check lang naman natin isa-isa. So, going back siguro, ito, better example. So, alam natin yung inner for loop is goal niya is mahanap yung minimum. So, yung current minimum, siya yung current minimum nung mga na-check mo na. And ano yung mga na-check mo na? So, starting from 47, and then, kasi sasama mo na si 36, tapos si 36 na yung minimum. Pag sinama mo si 26 na yung minimum. And then, moving on, si 26 pa rin yung minimum. And lumalaki yung list na siya yung minimum. So, parang A at J is the minimum, or J bar I is the minimum from A dot current minimum pala siya. So, the current minimum is the minimum from A starting from I to, let's say, J. Let's say I yung simula dito, J yung current ko na check. And actually, yung ganitong form is medyo pareho din siya sa insertion sort. Kasi kung titingnan mo, Okay. So, yung outer loop invariant siguro obvious naman na sorted from this from the start hanggang doon sa uh, let's say I sa gitna or last sorted index as indicated sa pseudocode dito. And when mag-i-insert tayo ng bagong element, si 27 magiging minimum, magkakaroon ka ng dalawang hati basically doon sa sorted na list. So elements na mas malaki sa kanya and mas maliit sa kanya. So alam natin si 27, siya yung minimum doon sa mga na-check ko na. So yung inner for loop mo would look something like yung 27 is the minimum from, since si J yata yung huli natin chine-check pababa, from the J hanggang I. Let's say I yung location niya originally. So yung sub-array na from J to I, si 27 siya yung minimum. Then si J, mag-decrement siya by 1. So, and then, ayun. So, loop invariant pa rin siya. Tapos si J, lumiliit ng lumiliit. Then, eventually, mangyayari yung case na hindi na siya yung minimum kung idadagdag ko si 26. So, i-insert ko na siya doon sa list. So, ayun. Sa bubble sort naman, yung inner na for loop, pwede mong i-observe pag i-sort mo siya kung ano ba yung element na dumarating sa dulo, siya yung largest element na so far. So you can say dun sa inner for loop na yung loop invariant mo has something to do with the maximum number. So may index I na chine-check dito. So possibly AI is yung maximum from the start ng array up until dun sa chine-check mo currently, or I-1. So, and then you can check it at each point dun sa loop. So let's say si 44 yung nasa I. So 44 is maximum from, or basically largest siya doon sa mga previous na numbers. And kahit at any point dito, as long as you pause it after the loop, let's say now, si AI is now 47 and siya na yung maximum dun sa mga nadaanan na items. So, pwede yun na yung inner na loop invariant mo. And then yung outer loop invariant mo naman, since ayan, nakikita mo naman, meron tayong sub-array na nasusort after each run. So, yung form niya is something like A from, kanina yata dyan ko, J hanggang end ng list is sorted. So, paano mo mapuprove na sorted siya after each iteration? Gagamitin mo yung inner na for loop. Since alam mo yung mga items mo from J to N, sila yung maximum elements based dun sa inner na for loop. Pag nagdagdag ka nung next maximum, nandun siya to the left ng mga previous maximum numbers. So sure ka na sorted pa rin yung array. So I guess bakit ko inaano yun, kasi dito sa second part, yung hint nyo dito is this is a sorting algorithm, and then may inner and outer loop invariants kayo. So again, yung inner loop invariant mo most likely has something to do with yung minimum or maximum in a section of the array. And then yung outer loop invariant nyo naman has something to do with a portion of the array that is already sorted. So, ayun. I actually think medyo baka mas madali ito doon sa mga binigay na problems sa week 4 na exercises. So, pwede nyo siyang gawin muna. Or kung baka madala kayo ng momentum, pwede nyo ituloy-tuloy from after answering the problem set, tuloy-tuloy nyo na hanggang dun sa week 4 exercises. Since parang pag nagpo-prove ka kasi parang nakukuha mo yung nadadala ka dun sa momentum nung pagsusulat. Well, baka ako lang yan. Okay, next is part 3, yung regarding recursion and divide and conquer. So ito, we have an increasing function wherein alam natin nag-increase siya indefinitely. Ang problem dito is hindi mo alam hanggang saan si f of x. So they're actually well, yung naive approach is just evaluating each hanggang mag-positive siya at O of n. But you want to find an approach kung saan hindi mo kailangan i-check isa-isa. So, yun nga, yung hint dito is you have to use divide and conquer. Pero ano yung i-divide ko? Or maybe, instead of division, you'll need multiplication. So, kailangan natin mahanap yung point kung saan nag-cross siya doon sa 0 or yung first element na positive siya, which is equal to 7. So, pwede kong i-check isa-isa, yun nga. And then, pag nag-positive siya, yun, nakahatop na. Pwede ako mag-skip. Mag-skip ako na isa. Nakita niyo ba yung cursor ko? So, pwede ako mag-start dito. Tapos mag-skip ako na isa. And then mag-skip ako ng isa. Mag-skip ako ng isa. And then check ko na lang kung negative yung nasa likod ko. Si 7 na yung hinahanap ko number. So, basically, nag-skip ako ng dalawa. So, what if mag-skip ako ng 3? And then 1, 2. So, nakita ko na positive siya. So, pwede akong bumalik ng isa. Or, pwede ko na lang i-check lahat nung nakaraan sa kanya. Kung naging positive na ba siya or hindi. But, since we're skipping by 3, parang, ayun, na-divide ko by 3 yung hinahanap ko. Pero n over 3, linear pa rin siya. So, paano kaya yung pwedeng gawin para maging linear time siya? Yeah, so, hindi naman ako pwede magsabi ng more than that kasi baka makuha nila isa. Anyway, moving on. Also, related din sa problem na to, alam nyo ba yung maybe nakita nyo online, kung may tower ka, tapos meron kang itlog that breaks at a specific height. So, ano yung algorithm na yung least number of drops yung kailangan mo i-check para mabasag yung itlog? So, related siya dun sa problem na to. Then, dito is just looking at your understanding doon sa recursion. So, whenever you call f of a plus b, mako-call yung f of a minus b, depending on the situations over here. So, yung recursion tree, basically, ang ginagawa lang nun. So, if kinall ko si f of 3, 2, ano yung mga functions na mako-call? Ano yung functions na mako-call niya? So, sige, example dun sa first part, si 3, so si A, si 3, to si B. So, A is greater than B. So, mako-call si A minus B, B, tsaka si F of B, B. So, yun yung kaya may dalawang split dito. So, basically, ilalagay nyo lang ito doon sa left side. Pero of course, lalagay nyo siya for the values 3 and 2. Then, supposedly, if i-evaluate means recursion tree, makukuha nyo yung ang ginagawa ng function na to. Then, next is complete the recursive function below to return a list that consists of the negative numbers in a given list. So, ayun, mag-attach kayo ng Python file that finds the negatives of the list na in a recursive way. So, ayun. I don't think this is much of a problem. Dapat. So, ang key lang siguro dito is to word or understand the problem in a na lumiliit yung or define the problem define the problem with itself na smaller in form. So of course, pwede nyo naman applyan to ng divide and conquer. So finding, pwede kong hati-hatiin yung list tapos doon And then, ayun. So, depende sa inyo kung ano yung approach doon. I guess merong divide and conquer approach dito and then merong simple na recursive approach lang. Then, ayun. Basically, ito, ang suggestion ko lang dito is think of a certain value of A tapos expand nyo lang kung ano yun naman ito. So, same with the first part here. So, ayun, evaluate nyo lang and then you'll eventually get it. Then, yung last part ng problem set is with yung current week's topics. So, actually, doon na tayo sa next part dito sa basically, mag-rundown tayo noong data structures part ng course or yung pinaka-introduction nyo to data structures. So, in its simplest sense, ang isang data structure is, as the name suggests, it's how you structure your data. So, siguro, sa mga nagawa nyo pa, sa mga na-encounter nyo pa lang so far, yung data natin is just, tabi-tabi sila. May listahan ako, tabi-tabi yung data kong ano. And then, nagsaswap lang tayo. But, what if, ayun nga, paano mo yun ilalagay in your actual computer? How can you actually see it sa memory? So, yun na yun, isa na yun sa data, part na rin yung pagiging data structure. Paano mo siya ilalagay sa memory? And then, yung next part doon is, what if mas gusto kong makita yung data ko or mas useful yung data ko if hindi siya line? So, for example, meron naman examples later. Pero yun nga, what if hindi mas efficient if gawin ko siya siguro in a tree, kung wari may hierarchy. Or let's say graph, if for example, merong mga connections between my data. So, in a nutshell, ang week 7 ay linear data structures and then week 8 yung introduction to non-linear data structures. Or actually, mostly trees lang and then hashes. Kasi meron pang graphs later on. Pero, in summary, ang linear data structures, sila yung very simple and easy to implement. So, linear, so tabi-tabi lang. And then non-linear data structures are more complex but can be very efficient. So makikita nyo dapat yon with the materials for this week. So starting with linear data structures, you can look at the study guide. So yung first part dito is differentiating yung abstract data types and data structures. So Makikita nyo naman siya in this notebook here. So, yung abstract data type is a mathematical abstraction or collection of objects and the operation done on these objects. So, basically, abstract data type, siya yung pinaka-construct na tinitignan natin. So, siguro with an example here, yung dynamic list na abstract data type. So, a dynamic list, as the name suggests, is a list na kayang mag-change ng size. Kaya siya dynamic compared sa static na fixed yung size. So, ano yung operations in-associate natin sa dynamic list? So, we want to insert elements dun sa list. We want to delete elements dun sa list. And of course, we want to access yung kada element natin doon sa list. And then, may dalawang general na or dalawang popular na implementation for the dynamic list. So, the first is yung dynamic array, which is yung ginagawa sa Python or ginagawa internally ng Python, wherein yung elements natin are basically to get a group of elements, you get a group of memory cells na tabi-tabi. And yun, basically tabi-tabi talaga sila. So in a dynamic list, since yung linear siya, there has to be may element before and merong element after a certain na element. So basta linear line. So in order to access an element, since tabi-tabi lang naman sila, kahit kailangan kong i-access yung last element, basta alam ko kung ilan yung number of elements ko, since tabi-tabi lang naman sila, kaya ko alamin yung memory location ng last element ko given yung memory location ng first element. So for example, an integer takes 8 bytes or uses 8 bytes. So I think it's a 32-bit system. So 8 bytes for an integer. If meron akong 10 integers and then so if I have 10 integers and then yung memory location ni first element is usually hex siya. So 0x000, yung memory location ng 10th element is 0x00, I guess 10 times 8. 5, 2. Well, yung first element will be OX00, so yung second element is OX008. So ito yung second, third, then fifth. So basically, it's, well, ako hindi kasi ako sanay mag-add ng hex. So, mahirap siya for me. Pero ang computer, madali lang naman sa kanya mag-add. And then, since alam niya na 8 bytes per element, so yung 10th element by simple multiplication, madali lang makuha yung memory location niya. So yun lang naman yung basically issue natin with access. How to find it in your memory. Kasi if we assign a variable name for each memory cell, parang may hirapan tayong mag-keep track. So, ang kailangan lang natin nalalahanin yung first element, yung memory location ng first element, and then madali lang for us to get yung maximum. Now, next is if we want to delete an element. So, for example, didelete ko si 20, kailangan kong i-shift yung elements ko so that, ayan, yung indexes ko would reflect it. So, ang worst case dito is when I need to delete yung first element, so kailangan kong i-move lahat ng other elements by 1. So, kaya yung worst case time niya is O of n. Same sa insert. Pag mag-insert ako dyan, kailangan kong igalaw lahat ng elements ko. So, it's O of n. Then, ayun nga, well, this is just because limited yung memory natin. So, it's what you call reallocation. So, more on that when you look at this topic more. So, yung other example dito is, so yung dynamic list, tabi-tabi sila. Si linked list naman, pasapasahan sila. So, the first element has a pointer to the next. And then that element has a pointer to the next element, and so on and so forth. So, ano yung advantage ito? Hindi mo kailangan alamin kung gaano karami yung elements na kailangan mo i-store. So, parang dito sa... Kasi you're only given a certain amount of memory ng computer. So, kailangan mo sabihin kay computer. Hindi mo naman pwede sabihin kay computer, kailangan ko ng basta maraming data. Basta bigyan mo na ako ng data. Hindi nyo naman gagawin yun. So, you have to specify, kailangan ko ng 32 bits of data. And then, ang ginagawa kasi ng dynamic list, kung wari, maghihingi siya muna ng 32 bits. And then, napuno na yon. So, ang gagawin nung program mo is maghihingi siya ng 64 bits. Tapos, ika-copy niya yung elements niya doon. And then, isasolve niya yung 32 bits na una niyang hiningi. So, for the linked list data structure, kukuha ko ng 1 bit at a time. Now, hindi na necessary for me to nagawing tabi-tabi yung elements. Ang gagawin ko na lang, yung first element ko, kailangan nyo na lang alamin kung nasaan yung second element ko. And then yung second element ko, kailangan nyo alamin kung nasaan yung next element ko. So, basically, yun yung idea behind the linked list data structure. Although ayun, para makarating tayo kay index 4, kailangan natin tanungin si index 3 kung nasan siya. Pero para alamin kung nasan si index 3, kailangan kong alamin si index 2. Para alamin si index 2, kailangan kong alamin si index 1. And para alamin si index 1, kailangan kong alamin si index 0. So, yung access ng ating list is actually O of n. Actually, ang advantage dapat is madali na lang dapat mag-insert. Although, kailangan kasi natin i-traverse yung list. And then, ayun, pagpapalit-palit ko lang yung mga arrows and makapag-insert na ako. So, essentially, if hindi ko kailangan mag-traverse, yung insertion operation ko is actually very fast. And hindi ko na kailangan mag-rewrite ng data. Ang kailangan ko lang i-rewrite is pointers. So, same with delete. And then, yun, meron. So, this is a case na isa lang yung pointer. Doon na siya sa next. Meron tinatawag na double linked list na instead of pointing din sa next, may pointer din sa previous. So, you can also do that. So, if we compare them, ang dynamic array, actually makikita mo, best siya sa access, pero O of n yun insert and delete. Sa linked list, O of n lahat. So, bakit pa tayo gagamit ng linked list? So, hindi naman pareho kasi ang O of n, di ba ang drawback niya is that it always takes into account the worst case. Pero magkaiba kasi yung mga worst case scenarios ng insert at saka ng delete. So, for example dito, if kailangan natin mag-insert doon sa start ng isang linked list, O of 1 lang siya. So, kung mag-insert lang ako kay index 0, kailangan ko lang yung bago kong element, kailangan ko lang siyang i-point kay index 0 and then na-insert ko na siya sa dynamic array, kailangan ko pang maglipat-lipat ng elements. So, kaya, ayan. So, when you insert and delete sa start, O of 1. When you insert and delete sa end, O of n. In contrast, ang dynamic array, ang delete at the end is O of 1. Ang insert at the end, at the worst case, is O of n. Pero, yun nga, O of n lang naman siya if kailangan natin mag-reallocate. Then, doon din naman pumapasok yung double linked list, pati sa end, O of 1 siya. Since may pointer din tayo sa dulo ng list. So, yan. So, kailan mo gagamitin yung linked list? So, if madalas kang mag-insert at saka delete sa simula, actually, mas magiging efficient siya sa dynamic array. So, yun na yung main part for, ito na actually yung main point ng linear data structures. Hindi ako makabalik sa study guide. Then, next is yung more data structures. Looking at this lecture notebook. So this is exploring yung stack, queue, and deck ADTs. So, ayan. So basically, ang stack is first in, first out. Ano yung una mong ilagay sa stack, siya yung una mong ilalabas. And then, for the queue data structure, ang una mong ipapasok, siya yung una mong ilalabas. Tama ba? So, the stack is first in, first out. Una mong ipapasok, last mong ilalabas. And then, the reverse is sa queue. Una mong papasok, una mo rin siyang ilalabas. So, difference dito doon sa original na dynamic list na data structure is wala tayong access doon sa middle elements. So, meron lang tayong access doon sa either last element na pinasok sa stack or yung first element na pinasok sa queue. So, technically, mas simple siya. And then, for example here, in summary, ang linked list operations natin, or when we implement this stack as a linked list, O of 1 lahat ng operations natin. Kasi kailangan lang naman natin mag-operate dun sa dulo. So, and after naman ng queue, meron tayong tinatawag na deck or doubly ended queue. So, excuse me. Pwede kang mag-insert sa front, pwede kang mag-insert sa back, pwede kang mag-pop sa back, sa front, pwede kang mag-pop sa back. So, parang combination siya ng, obviously, dalawang queue. Meron kang queue na paharap, meron kang queue na pabalik. So, pwede kang maglagay at the back or at the front. So, yun nga, ang main point dito din naman is, and makompare mo, if depending on the implementation na gagawin mo, mag-iiba yung running times ng operations. Although, ayun, looking at it, bakit ba yung magkakaroon ng queue or ng stack kung meron namang deck na kaya niyang gawin pareho? So, ang pinakamalaking reason for that is that hindi naman pwedeng laging may deck. So, what if meron lang sa'yo queue, meron lang sa'yo stack? Kasi ang advantage ng queue at saka ng stack, they're very simple. Hindi natin kailangan i-access yung nasa gitna. So, parang isang memory location na yung kailangan natin tandaan. So, kung sa linked list, kahit hindi na natin pansinin lahat ng memory locations sa ibang elements, since ang nagmamatter lang naman sa kanya is yung first element, yun lang yung kailangan natin tandaan. And then, yun din yung mas madaling i-implement in hardware So for example, ang ang program stack or yung memory stack natin when we're calling functions, it's actually a real stack. It's implemented in hardware. And then when you go to your future EEE subjects, lalo na sa embedded systems, stacks lang yun available sa inyo in memory. So, knowing how to deal with stacks or maybe queues, kung queue lang din yung available sa'yo, uh, can make it, basically, for example here, yung dalawang stack, pwede ko siyang gawing queue. So, given enough creativity, ma-implement mo yung isa with another. But, ayun, we can't always rely on having the best na data structure na alam natin. Kung ano, ang stack queue at saka deck, pwede naman silang gawing dynamic list na lang. Pero what if hindi available yung dynamic list? So, hindi mo na alam yung kailangan mong gawin. So, kailangan mo pa rin aralin yung mga stuff na to. So, basically, yun lang naman for this part. But again, in summary, yung operations natin on a linear na data structure, medyo limited tayo. Either O of 1 or O of N lang siya. So, what if lahat ng mga kailangan natin gawin should be efficient? What if di ako maka-afford ng linear time for any of these? So, doon papasok yung non-linear na data structures, which is yung sa week 8. So, ang week 8, ang focus niya is on non-linear data structures. And then, so yung first na titingnan natin is yung trees. So, ang tree na data structure, as the name suggests, ayun, meron tayong tinatawag na, actually ito is an example of a tree. Yung thing right here. So, instead of just having a line, i-arrange natin in such a way na may information na tayo given yung placement pa lang nung item doon sa list. So for a tree data structure, ayan, meron kang root, tapos meron siyang children, which are also trees. So a tree is a node wherein it has several subtrees. So a subtree is a node with subtrees. So medyo recursive ang definition niya. Which is why madalas din actually yung recursion sa mga functions na kailangan gawin. So, some terminologies. So, root, yung tinatawag doon sa node na walang parent. So, example here, meron tayong tree. So, ang root node si A, wala siyang parent. And then, meron siyang 4 na subtrees. Subtree B, C, D, at saka E. And then, si B, meron din siyang subtrees na F and G. So, ayun. So, si A, children niya si B, C, D, and E. Si B, C, D, and E, parent naman nila si A. So, parang family tree lang. And then, extending it, meron din concept of ancestors and descendants. So, si A, wala siyang ancestor kasi wala siyang ninuno. So, in this case, si U, marami siyang ancestors. Si S, O, I, C, at saka si A. So, lahat ng related sa kanya. So, yun yung ancestors and descendants. Degree of a node is the number of its children. So, si A may 4 na children. So, ang degree ni A ay 4. Ang degree ni E ay 1. Degree ni D ay 3. The depth of a node is yung length ng path from the root to the node. So, basically, gaano siya kalalim or gaano siya kalayo sa root. Pang ilang generation na siya when we talk about family trees. So, si A nasa depth 0 siya since wala siyang yun na siya. Siya na yung siya na yung, siya na yung root. Si B, si B, C, D at E, they're at depth 1 kasi ang distance nila from the root node is 1. For example, si U, ang depth niya ay 1, 2, 3, 4, 5. So, 5 steps bago makarating kay U. So, you can say 5th generation or may depth of 5. Ang height naman ng node, the inverse, ano yung longest na path papunta, ay longest na path na ma-generate mo from that node to a leaf node. So, ang leaf node ay basically walang node na walang children. Tapos, internal node naman yung otherwise. So, then, so, si U, ang path, ang depth niya ay 5, pero ang height niya is 0. Si A, ang depth niya ay 0, ang height niya ay 1, 2, 3, 4, 5. So, ang path naman is a sequence of connected nodes. Actually, kanina ko binabanggit. So, ang unique sa trees, walang, to get to a node, isa lang yung path na pwede nating daanan. So, to get to node P, ang kailangan mong daanan is DK at saka P. So, that is something unique sa trees, na isa lang yung path natin na kayang daanan to reach any node in the tree. So, applications of trees, file systems, syntax trees, so kung ano yung gagawin ng isang program, and binary trees. So, binary trees is a tree wherein yung maximum degree ng isang node is 2. Kaya siya binary. Kasi 2. So, some terminologies, a complete binary tree is wherein all levels are completely filled except for the last level. So, ang tinatawag natin na level is lahat ng nodes na pare-pareho yung depth. So, since binary tree siya, meron tayong maximum number of nodes per level. So, at level 0, isa lang. At level 1, dalawa. At level 2, hanggang 4. And then at level 3 hanggang 8. So, basically, 2 to the level yung maximum number of nodes in a level. Then, ang full binary tree naman is that when all nodes possess either 0 or 2 children. So, yung degree ng ating nodes, either leaf node siya or meron dapat siyang dalawang anak. So, ito on the left is a complete siya since lahat ng levels ay filled except yung last node, ay yung last level. But since si C dito, ang isa lang yung child niya, so, hindi siya degree 2, so hindi full yung binary tree. Then, next is a perfect binary tree is when all the nodes contain exactly 2 children other than the leaf nodes. Parang pareho lang yun sa full. Anyway, so, more specific example ng binary tree is a binary search tree. So, yung binary search tree natin has a certain property wherein yung left subtree ko contains nodes that are always lesser than the node's key or whatever yung value niya. So, in this case, si 8, lahat ng nasa left ni 8 ay less than 8. Lahat ng nasa right ni 8 ay greater than 8. And then, yung mga subtree ko, of course, should be binary search trees as well. So, and so instead of having a list na plain na diretso, ilalagay ko na yung mga elements ng list ko in a way na parang may arrangement sila. So that when I search for an element, alam ko na yung pupuntahan ko. Kung wari kailangan kong hanapin si 4, alam ko nasa left siya ni 8, nasa right siya ni 3, nasa left siya ni 6. Kasi 4 is less than 8, greater than 3, and less than 6. So, para siyang binary search. Pero hindi na natin kailangan mag-partition or hindi na natin kailangan alamin kung nasan yung gitna. So, kailangan lang natin mag-traverse ng tree. So, by arranging the elements in a certain way, kaya natin speed up yung mga operations natin. So, ano yung runtime ng search? So, it depends doon sa height ng tree natin. So, si 8, in this tree, ang worst case na search time natin is 3. Kasi, yun na yung height ng tree. Basically, pwede mo rin count yung ilan yung longest path. So, at the worst case, it will take 1 to 3 jumps para mahanap yung isang item. Now, of course, pag mag-insert ka dun sa tree, can check Visualgo. So, for example, this tree na to, mag-insert ako ng node 27. So, starting sa 41, less than siya, greater than 20, less than 29. Doon ko i-insert si 27. So, ang insert operation natin, since kailangan natin daanan lahat ng nodes, and at the worst case, dadaanan natin lahat hanggang sa terminal or hanggang sa leaf node, so hanggang sa last level. So, yung running time or worst case running time natin would be O of or linear with respect sa height, and then most ideally with respect to log of h, ay log of n. And then same with deletion. So if we want to remove an element, let's say 99, kailangan natin traverse yung list. So pupunta doon, and then tatanggalin siya. So yung traversal actually, or yung pagpunta doon sa current node, siya yung nagtitake ng time. Which is why yung time complexity natin is always related dun sa height ng isang binary search tree. So in the worst case, you can have what we call a skewed tree na nasa left lahat yung elements. So para lang siyang linked list. So in this case, yung height natin is equal to the number of nodes. So magiging O of n. Now may tinatawag din tayong AVLT na self-balancing. So, pagka nag-insert tayo ng element na magiging unbalanced yung 3, let's say, insert ako ng 3, number 3. And then, insert ako ng 2. So, pag nag-insert ako ng 2, para magiging heavy tayo sa left, so may gagawin na tinatawag na rotations yung 3 such that yung balance natin is maintained. So in this type of with some modifications doon sa code ng binary tree, we can achieve yung O of h or O of log n na time. So ayun, ang disadvantage din ng non-linear na data structures when compared to linear na data structures is paano natin dadaanan lahat ng elements? What if gusto kong malaman yung laman noong aking tree? So, masyadong madaming paraan, basically. Pag linear data structure kasi, pwedeng left to right, right to left. Yun na yun. So, in a tree, there are several ways. And usually, for non-linear data structures in general, meron tayo yung tinatawag na depth first search or breadth first search. So, unahin ko mo yung breadth first search kasi isa lang naman yung example niya, or tinatawag na level order na traversal. When we say breadth first, lahat ng magkaka-level siya yung iuuna ko. So, when we have a level order traversal nung tree na to, magsa-start ako sa topmost level, 15. Then, next level, 6 and 50. Then, next is 4 and 7. So, as you can see, 4, 7, 23, and 71. So, as you can see, level order traversal, so per level tayo kumukuha nung or per level natin piniprint out yung elements. So, breadth first search siya kasi as you can see, starting from dun sa narrow, lumalapad tayo. So, lumalaki yung breadth. Yung isa naman is yung depth first search wherein instead of palawak kang ganun, palalim ka muna and then babalik ka na lang so lalalim ka ulit. So, babalik ka ulit. So, for a binary tree, meron tatlong different methods to do so. Yung in-order traversal is mag-traverse ka muna dun sa left and then punta ka sa leftmost and then pag napuntahan mo na yung sa pinaka-left, yung current na node and then yung nasa right. So, basically, yun yung difference ng tatlo. Kailan ka nag-ooperate doon sa kung nasaan ka. So, pwede kang mag-operate doon sa node after nung sa left, before nung sa right, or mauna ka before nung 2 items, or mahuli ka before your children. So, tatlong combinations. So, yung in-order traversal nitong nasa taas is, since mauna tayo sa left subtree, pupunta tayo kay 6, mauna tayo dun sa left subtree ni 6, which is 4. Mauna tayo dun sa left subtree ni 4, which is wala. So, after nung left subtree ni 4 is si 4 itself, and then yung right subtree ni 4. So, yung right subtree ni 4, that's 5. Pupunta siya sa left, wala na. So, babalik siya sa node, then 5, so 5. And then, pupunta siya sa right, which is wala na. So, babalik na siya. And then, babalik siya ulit kasi tapos na siya. And si 4, tapos na rin siya. So, since tapos na yung nasa left ni 6, it's time for 6. Then, doon sa right naman ni 6, which is 7. And then, yung sa left ni 7, which is wala. So, wala akong gagawin. So, tapos na yung nasa left ni 7, lalagay ko na si 7, and then yung nasa right naman ni 7, which is wala. So, tapos na si 7. So, tapos na si 7, tapos na si 6. Tapos na yung nasa left ni 6, tapos na si 6, tapos yung nasa right ni 6, pwede na siyang bumalik kay 15. And then, actually, ang in-order na traversal sa isang binary search tree would result in a sorted list. So, ang pre-order traversal naman, magsa-start tayo by printing or visiting yung node itself. So, ang pre-order dito sa taas, mag-start ako kay node 15. So, lagay ko muna si node 15. And then, punta ako sa left niya. So, yung left niya is 6. So, lagay ko muna si 6. And then, punta ako sa left niya, which is 4. So, lagay ko muna si 4. And then, punta ako sa left niya, which is wala. So, balik ako. And then, punta ako sa right, which is 5. So, tapos na si 5. Pwede na bumalik. Tapos na si 4. Babalik na sa 6. Tapos, pupunta naman kay 7. And then, since wala na si 7, balik kay 6, balik kay 15. So, tapos na si 15, tapos na si 6, doon tayo sa right niya, which is 15. And then, after ni 50, yung left is 23, and then 71. So, yung post order, baliktad. Punta muna ako sa left, punta muna ako sa left, punta muna ako sa left, wala pa. Punta muna ako sa right, 5. And then, since tapos na yung left and right ni 4, tsaka ako pala lalagay si 4. And then, tapos na si 4, so si 7 balik kay 6, pero bago si 6, si 7 muna. And then si 6. And then si 23. then si 71, and then si 50. Okay, so meron bang shortcut dyan? Well, hindi naman siya shortcut, pero one way to do it is maglagay ka ng dot. Pagka pre-order dito sa left, pag in order dito sa gitna, pag post order, let's see, gawin natin ibang color. Pag in order dito, so ito yung in order. Ang yung color kanina. So let's say ito yung post. Then, ito ba? Let's just say ito na lang yung pre-order. And then, starting dito sa left, mag-trace ka lang ng line. And then, for example, sa pre-order, nasa left siya ng mga nodes. So, pag nadaanan mo na yung left, ipiprint mo siya. So, I need my mouse. So, dito, una natin nadaanan si 15, and then si 6, and then si 4, and then si 5. So, yun yung first 4 sa pre-order. Pero, when you go in order, ay, mali. Yung dot natin is dito sa baba. So, pag ituloy ko yung line, so if itutuloy mo yung trace, una mapiprint si 4, and then si 5, and then si 6, and then si 7, and then si 15. So, basically, kung kailan madaanan yung dot, doon mo ipiprint out yung isang element. So, siguro, for a clear example, if gawin natin lahat yung, lagay ko yung dot sa gitna ng lahat, and then gawin ko yung pag-trace starting from the left. So, una kong madadaanan si 4, then si 5, 6, 7, 15, 23, 50, 71, and done. So, since nasa gitna yung mga nodes, in order siya. And then, if gusto ko yung pre-order, susundan ko yung mga unang tumatama sa kanan. Kaliwa pa. Ayan. Meron pa to dito dapat. Yeah, so kailangan matrace mo talaga yung. Yeah. Mas gets nyo to pag meron ng whiteboard. Pero sige. Hopefully na-gets nyo yun. Anyway. So yung tinatawag nating traversals para madaanan lahat ng elements ng tree. At least once. So meron sample implementation dito. visualgo.net, may visualization. And then nandito rin yung tinatawag na predecessor and successor. So basically, ang predecessor, for example, 7. Before 7, ang predecessor niya is 6. So basically, if mag-in order traversal ka, which element is before that element. So, ang predecessor ni 15 is 7. So, meron namang pseudocode dito. So, basically, pag gusto mo makuha yung predecessor ni 15, hanapin mo yung element na mas maliit sa kanya na pinakamalaki. Since ang in-order traversal natin sorted siya, di ba? So, yung greatest element na less than 15, siya yung predecessor. Yung smallest element na greater than 15, siya yung successor. Then, next sa binary search trees ay yung tinatawag na heaps na pwede mo rin siyang i-view as a tree. Oops. Okay, actually ito na. So, ang binary search tree, lahat ng mas maliit sa kaliwa, lahat ng mas malaki sa kanan. Ang binary heap ay lahat ng mas maliit ay children, lahat ng mas malaki ay parent. So, sa binary search tree, smallest is nasa left, greatest is nasa right. Sa heap, greatest or ang max heap, greatest sa taas, least sa baba. Pag min heap, baligtad. Minimum sa taas, maximum sa baba. So, minimum heap, pinakamaliit sa taas, pinakamalaki sa baba. Pag max heap, pinakamalaki sa taas, pinakamaliit sa baba. So, pag nagdadagdag tayo ng bagong element sa heap, first is let's say 60. So, first is ilalagay lang siya dun sa dulo ng heap. And then, i-compare siya dun sa parent niya. If mas malaki sa parent niya, papalit sila. And then, i-compare niya siya dun sa bagong niyang parent. If mas malaki, ipapalit sila. And then, i-compare siya dun sa susunod na parent. If mas maliit, stay the same. And then, ayun. Ano na tayo sa tamang location. So, ganun lang naman na pre-preserve yung yung heap property na tinatawag. And then, ang usual na dine-delete sa heap is yung root node. Kasi as you can see, since ang pinakamalaking number, siya yung nilalagay sa taas, yung root node natin will always be the maximum number doon sa heap mo. Kaya siya heap eh. If for example, meron kang heap of pebbles, magti-trickle down yung mga maliliit, magsi-stay sa taas yung malalaki. Tama ba? Oo, di ba? And then, ayun. So, pag ine-extract natin yung maximum, ayun, matatanggal siya. Mare-replace siya with the last element for simplicity. Actually, pwede naman kahit any element. Pero pinakamadali if yung last nating nilagay. You'll know why later. So, kahit anong element, pwede kong ilagay doon. So, after nun, i-compare ko na lang siya sa children niya. So, ko-compare ko siya dun sa mas malaking child, which is yung left. And if mas maliit siya, magsaswap sila. And then, ko-compare ko siya with its new children. And then, dun sa max, isa-swap ko siya dun sa mas malaki. Ko-compare ko sa children niya, mas maliit. So, ayan. So, ganun lang naman. So, bumababa siya. Yung tawag doon is heapify down or bubble down. Pag yung umakit kanina is heapify up or bubble up. Hindi ko lang sure kung nandito yun. So, very useful yung heap when making a priority queue. So, pag nag-insert tayo, pumupunta yung greatest priority dun sa taas. So, notice na nagdadagdag tayo parati from the lowest level starting from the left pa kanan. So, we're trying to maintain a full, tama ba? Full or complete? So we're trying to maintain a complete binary tree. Bakit? You can see here is merong mga numbers sa baba. So technically, yung tree na structure na to, pwede ko siyang ilagay sa isang list. Linear na list. Such a way na si index 1 siya yung root node ko, si index 2 at saka si index 3 siya yung children ko. So pag minultiply ko ng 2 yung current index ko, mapupunta ako dun sa children niya. Times 2 plus 1. Si 3, pag minultiply ko sa 2, 6. Tapos times 2 plus 1, 7. So yun yung magiging index ng children ko. So dahil sure tayo na full binary tree siya, yung magiging index ng mga susunod ko na elements will always have that index. So kaya kong ma-predict yung children ni index 6 will be at index 11, index 12 at saka 13. Kasi alam ko, full yung binary tree. Kaya, kaya pag nag-insert tayo ng, or pag nag-extract tayo ng isang number, kinukuha natin yung last element. Kasi pinakamadaling mag-extract or pinakamadaling mag-delete ng isang element from the end of the link at the end of our list. So, actually, you can compare. Itong binary search tree natin, medyo parang linked list yung approach niya sa kanyang implementation dito sa baba. So, meron tayong left dot right. So, pag linked list, meron tayong next tsaka previous. So, in this case, meron tayong left dot right. Pero for a binary heap, pwede natin siyang ma-implement using a dynamic array. So, ayun. So, parang medyo bumabalik-balik pa rin sa 2 yung main data structures natin na linear. So, parang minumod, nagdadagdag lang tayo ng meaning doon sa position nila in the list. So, sa binary search tree, yung meaning ng location nila, pag nasa left sila, mas maliit. Pag nasa right sila, mas malaki. Sa binary heap naman, pag parent ka or mas nasa taas na level ka, mas malaki ka doon your children. Although, pwede natin tingnan dito, hindi naman lahat na magkaka-level, hindi naman ibig sabihin nun sila yung magkaka-level, basically. Kasi here, C1, nasa level 2 siya, pero hindi siya yung least na number. You'd expect kasi, di ba, maximum sa taas, minimum sa baba. So, ang kailangan lang naman kasi masatisfy, mas maliit ka sa parent mo. So, si 1 mas maliit kay 26, so tama siya dyan. And then si 1 mas maliit siya kay 36, so tama lang din siya dyan. So, si 2, mas maliit ka siya kay 7, mas maliit siya kay 25, mas maliit siya kay 36, so tama lang na nandyan siya. Hindi naman kailangan mas maliit siya kay 1, since hindi naman sila related pagka ganyan mo sila in-insert. So, you notice that the way yung order ng pag-insert yun ng element sa heap can result in different na setups or mag-iiba yung magiging final na kalalabasan niya. So, ayun. Ano pa ba yung masasabi ko tungkol doon? So, since yun nga, hindi naman tayo assured na yung minimum element nasa baba, walang given yung screenshot ng heap na to, kahit anong traversal na gawin mo, hindi ka magre-result in a sorted na list. Pero yun nga, laging laging maximum element yung nakikita mo dito. So, ayun, there is a way to sort a list using a heap, pero it's not with a traversal. Not unlike yung binary search tree. Pag nag-in-order traversal ka, meron ka ng sorted na list. So, ayan, may masasabi pa ba ako? Actually, yun lang naman yun. So, you have optional materials here. that you can look at if hindi enough yung mga notebooks tsaka yung video playlist here. Assessment natin is you have one formative quiz on the binary tree definitions. So, medyo ako rin yung gumawa. So, usually, ano lang naman siya, testing if you understand yung ibig sabihin ng complete, full, tsaka balanced. Wala yatang balance dito. So, a balance tree is yung pag-difference no heights ay at most 1. And then skewed. And then yung traversals. So, yun yung sa binary tree definitions. And then for the summative quiz, medyo expect an essay part na related dun sa mga trees. Tsaka, ayun pa pala, yung last part is meron tayo na tawag na hash table. Unfortunately, walang lecture notebook for this. Pero ang closest analog ay yung closest thing na na-encounter nyo, and actually hash table din siya talaga, is yung dictionary sa Python. So, you can watch this video naman on your own time. So, basically, ang ginagawa sa hash is ina-associate yung dito. Ay, tumigil. Ang point ng hash table is i-associate mo yung isang key mo with a memory value. Siguro gagamit ka ng function na itra-translate mo to a memory value yung isang item. So, basically, parang mapping siya. Kumbaga. So, ayan. You can look at here for more information. Pero, yung mostly point niya is mapapabilis yung memory access mo assuming na yung set of data mo is or maganda yung function mo. So, can't seem to have a good example. Okay. So, ayan, meron kang tinatawag na key that indicates saan mo siya ilalagay dun sa table, and the hash function that converts the key to a certain number. So, for example, ang gusto mong i-store sa data mo has a key 4, ipapasa mo siya dun sa function and magre-return siya ng number. And that number determines kung saan mo siya ilalagay doon sa isang list. Meron ba dito example? And so for example, meron kang 4 students or 4 persons here. Pwede kang gumawa ng hash function regarding their names. Hindi ko siya makontrol. So here, pwedeng kunin natin yung length ng name ng person and then mag-add ng 1 pag male siya and then modulo 6. So, pag stinore natin siya in data or yung magiging resulting hash function, parang yun yung magiging index niya doon sa ating list. So, basically, it's a way to associate something doon sa data mo to a memory location. So, kaya siya parang tinatawag sometimes na hash or mapping. So, may dadaanan ka na hash function and then mamamap yung data mo to a certain memory value. So, of course, yung mahirap dito, what if two of your data entries pareho yung na-return na hash function? So, hindi naman sila pwede mag-share ng same memory location. So, ano yung ginagawa doon? Yung first is, yung most simple way is to do yung tinatawag na separate chaining, wherein pag same yung hash value, ilalagay mo siya. Ayan. So, ito yung example na how to you set up your hash table. So, yung table mo, since given yung hash function mo, meron kang 6 possible na outcomes, meron tayong 6 different memory locations na associated doon sa hash values na yun. So, sa first example dito, si Will, age 31, and yung answer no hash is 3. So, lalagay mo siya doon sa index na 3. Si Leah naman, mapupunta siya sa hash na 4. So, yun. So, other people. So, ano yung advantage nito? For example, gusto kong mahanap yung entry na merong pangalang Will. Since alam ko yung mag-hash siya to 3, check ko lang yung index 3 for the value of Will. Hindi ko na kailangan i-check isa-isa yung elements kung yung laman ba nila talaga ay Will. So, it can speed up yung access time natin. So, in that case, from checking each item one by one, dadaan lang ako sa hash function, alam ko na kung nasa ang memory location siya. So, from something na O of N na search, maging constant time siya, depending dun sa hash function. Pero yun nga, ang problem nga is what if multiple names is mahash dun sa same na number? So, when we say separate chaining, gagawa lang tayo ng chain, or in this case, parang linked list. So, pagka merong Leah, and pag gusto mong mahanap si Leah, mapupunta ka sa 4, so magkakaroon ka ng linear search doon sa chain ni Leah. And then, and eventually, yon, so dumadagdag yung chain. So, even though pareho yung hash value nila, since alam, isa-store din naman natin yung actual name. So, pwede pa rin naman tayo mag-search among them. So, yeah. So, that is basically hash tables with chaining. So, if of course, kailangan pa ng more information, daanan nyo lang yung videos na ito. So, ang required lang naman dito is yung first 2 videos. Although helpful din naman yung ibang videos if you have the extra time. So, yeah, that is for the materials dun sa weeks. And yung optional na problem set naman, pwede rin natin silipin. So, this is optional. So, pwede nyo hindi sagutin. Pero, actually, we're thinking of making it extra credit. So, titingnan na lang namin. We'll be having a meeting in pag sa start ng reading break to check yung if we need to adjust things dun sa course. So, for part 4, meron siyang dalawang major parts. So, the first part is you're given a scenario na kailangan mo mag-set up ng database na meron kang priorities na tinitingnan. So, you have to report the total number of vaccines per brand, identify the soonest expiration date among the donations, and find the donation entry based on a contact number. So you have to do that in better than O of n time. So anong data structures yung or paano mo siya dapat i-set up in your database para mabilis silang ma-access. So, and so basically, questions are how would you set it up, paano mo siya, basically prove, paano mo siya na-optimize, and then ano yung possible drawbacks ng setup mo. Excuse me. Yung second part is with binary tree rotations. So, one way to balance a binary tree is through rotations. And may kita nyo dapat dito kung bakit. So, yung first question, prove that after a rotate, ma-maintain yung BST property. And then, ayun. Makikita nyo dapat dito yung height ng ating sub-tree after a rotation is modified by some amount given yung locations ni A, beta, and gamma. And then, ayun. Kailangan nyo lang makita ano yung conditions wherein if initially unbalanced si tree and then nag-left rotate tayo, tapos naging balance siya. So, ano yung conditions nun? And then, prove that if mag-insert ako ng bagong element sa BST, I can balance the BST with at most 2 rotations. So, actually, makikita nyo yun dito when you look at the AVL trees. If mag-insert ako ng elements sa left ni 20, sa right ni 23 actually, 24, 25. So, add ako ng 24, add ako ng 25. So, meron akong 1 rotation para ma-balance siya. Then, if I insert, ano pa ba pwede? 22. So, insert 22. Insert 21. Hindi mo makakuha ng case ng dalawang rotation. Wait lang. Insert 2. Yeah, basta, actually, kahit na isa lang. So, actually, may case na kailangan ng dalawa. But, yeah, makikita nyo rin yan. And then lastly, provide at least the pseudocode for insert operation on a balanced BST, which will always result in a balanced BST. So actually, clue nyo na yung pseudocode dito. Although hindi reveal dito ano ibig sabihin ng mga cases na to. So actually, kung malaman nyo na kung ano yung ibig sabihin ng mga cases na yan, you can actually tell or you can actually have a pseudocode na noong sa number 5 dito. And optional lang naman siya, so you can do it on your own time. So, I guess that's it for this session. Hopefully may natutunan kayo. For any questions, just send me an email. Bye-bye.